This tutorial is the beginning of chemistry. We will be discussing atoms and molecules, inquiry, classification of matter, and the physical and chemical changes. So what is chemistry? Chemistry is the study of matter, including the changes of matter and the energy accompanying them. It's also to be considered the science that seeks to understand the behavior of matter by studying behavior of atoms and molecules. Everything in the universe can be broken into two categories, matter and energy. Matter has mass, which is the amount of matter, and occupies volume, which is space. We can further classify it by looking at what physical state it's in and how pure it is. Energy, however, has no mass or volume. It has the ability to produce change, and it can also be classified further, but this time with heat and work and things along those lines. Atoms and molecules are the basic units of matter. Atoms are the most basic unit of matter there is. It's the fundamental particles that are building blocks of ordinary matter. However, atoms are typically not found in isolation. They're found in molecules. Molecules are a group of atoms that are held together by chemical bonds. Think of this as Lincoln Logs or Legos, where each Lego is an individual atom. However, one Lego by itself isn't a whole lot of fun. It's only when you start stacking them together that it becomes more of a game. So let's take a look at the scientific method. The very first thing you're going to do is ask a reasonable question, and that's usually done by observation. From there, you want to do lots of background research. Otherwise, you wouldn't be able to come up with a hypothesis as to why you think something happens. A hypothesis is an educated guess as to why things occur. Then you're going to create and test an experiment. You're going to analyze what happens to be either reasonable or not reasonable. If it's false or partially true, you're going to try to think of another reason. A hypothesis won't be true, but our results might conclude that it's unable to be falsified. And then you report your results. Within this process, you'll be using a lot of variables. Keep in mind that math is used in almost every step of the scientific method. It's the tool of science. And along with math comes graphing. You'll have an independent variable, which is on the x-axis, and a dependent variable, which is on the y. So things like time could be on the bottom because you have no control on what the time is. And the things that are affected by that, or the things that are changing, are going to be on the y-axis. Experimentation allows the determination of cause and effect, and a lot of times it's expressed as a mathematical relationship. So what about if a theory comes about? Well, once you do the whole scientific method over and over and over again, and you seem to have fairly reasonable results that are repeatable, eventually that method is going to become a theory. There's a slight difference between theory and law. A theory is a well-tested hypothesis that explains what's happening. It's a model. It can be general and you can use to predict it. It can be validated by experimentation, but it can never be conclusively proven. So you see it happening over and over and over again, and you think it's Y, but it's not going to be 100%. Whereas scientific law is a summary of observations. So with the theory, you'll have an explanation. With the law, you will not. There will possibly be a mathematical relationship. And once again, you're going to be wanting to do a lot more research. Scientific law can be proven invalid by new data. So just because it's the law one day doesn't mean that enough research isn't going to occur to make a alteration to the law. Since we're on the topic of experimentation, let's talk about the properties of matter. Properties of matter are observable, measurable characteristics. We use them to describe, clarify, and identify what's going on. And they're either expressed qualitatively or quantitatively. Qualitatively, we're referring to a description. We typically won't use numbers to describe it. So these are things like color, smells, things along those lines. Whereas when we talk about quantitative, we're talking about some kind of numerical value that goes with it, such as mass or volume. To further explain the qualitative versus quantitative and the purity, we can also talk about the states of matter: solid, liquid, and gas. Notice how the pictures depict it. With a solid, it's not taking the size of the whole container. It's staying to itself and it has its own shape. Whereas the liquid, even if it's the same volume, it's spreading out throughout the bottom of the container. Gas, however, not only has the same volume, has the same amount of molecules, but they're spread out throughout the entire container. To look at solids a little bit closer, we have crystalline and amorphous solids. Crystalline solids have a very specific repeating pattern, where amorphous solids tend to be a little bit less specific. Going back to qualitative and quantitative, it's typically estimated and no measuring device is given. Whereas quantitative, you need a value, an actual number, and appropriate units. Make sure you use the units, otherwise you'll be confused on what the number actually means. You need to use a specific instrument, and you'll be learning more about that in the laboratory section of your class. So when we're looking at quantitative properties, we need reliable measurements, we need proper selection of the measuring device. So what instrument you use to determine the volume, what instrument you use to determine the mass is going to make a difference. You also want to make sure to use the appropriate units. We in the science world always use either metric or SI units. Never use English. We also use scientific notation, which we will discuss later. It's the ability to compactly express large numbers and small numbers. It makes it easier for us to communicate and easier for us to write. We also use dimensional analysis quite regularly, which is a way to convert units. It's also called the factor label method and the unit factor method. Other ways to describe properties involve intensive and extensive properties. Intensive properties do not depend on size, the extent, or the amount. They only depend on the identity, the purity, and conditions of the measurement, such as temperature and pressure. Extensive properties, however, do depend on the amount, and they are additive. So in other words, you can multiply, divide, add, and subtract them. You can deal with them with math. Different materials can have the same extensive value, but they cannot be the same intensive value. Properties are either intensive or extensive. They're never both. So let's go over some review of these. Color, since it doesn't matter how much is there in order to determine the color, that's considered an intensive property. Odor, same thing. It doesn't matter how much of the substance is there, it's still going to have the same smell. Mass is considered extensive because the quantity does depend on how much it weighs. Same with weight. Malleable, that just means you're able to shape it. And that would be intensive. Because it doesn't matter how much you have. Volume is extensive. Because the more you have, the more volume there's going to be. Melting point and freezing point are considered intensive. It doesn't matter how much there is there. Density doesn't matter how much you have, it's all going to have the same product. Hardness, same thing. The length is going to be extensive because the more you have, the longer it's going to be. And then finally, conductivity is going to be intensive for the fact that it doesn't matter how much is there, it's still going to be the same conductivity. So let's take a minute to talk about pure substances and mixtures. A pure substance is a substance that's made of a single atom or molecule. It can be broken into its elements and compounds. This pure substance can't be broken into elements and compounds. Elements are substances that cannot be broken into simpler forms. You'll find these right off the periodic table. A compound can be broken into two or more substances by chemical reactions. And those substances are the elements. Mixtures, however, are a combination of two or more pure substances. Homogeneous mixtures are two or more substances mixed together with the same composition. So in other words, no matter where you look at it, it's going to look the exact same if you're looking at it in the molecular level. They're also called solutions. So a solution is a homogeneous mixture. And they always stay in the solution. They do not settle out at any time. Heterogeneous, however, are substances with varied composition. So in other words, where you look at it is going to have a different molecule arrangement than wherever you look. And it does settle out over time. You're going to find layers. They're called colloids and suspensions. So just so you have a visual flow chart with this, we can divide all matter into two categories, mixtures and substances. Mixtures can further be broken down into heterogeneous and homogeneous. If they settle out, it's heterogeneous. If they don't settle out, if they stay mixed, they're considered homogeneous. Substances can be broken down into compounds and elements. Compounds are a combination of elements that are chemically bonded together. And then elements are the most pure things there are. So we can do a little bit of review with this as well, and breaking these down into element, compound, heterogeneous, or homogeneous. Jello, if you have Jello, whether it's a liquid or a solid, whether or not you've put it in the refrigerator, that doesn't matter. It's still going to have the same composition regardless of where you look at it. Mint chocolate chip, however, is considered heterogeneous. because the chocolate chips might be more condensed in one area than they are in the other. Same with chicken noodle soup. A lot of times the chicken noodles will actually fall to the bottom of the broth. Helium is an element. It's right off the periodic table. Water is actually a compound. Its chemical formula is H2O. So I know that 2 hydrogen and 1 oxygen are all bonded together. A diamond is actually a trick question. It's actually pure carbon, which means it is an element. Tea is considered a homogeneous mixture. No matter where you look at it, it's going to look the same. However, once you put ice in it, the ice floats to the top, making now it's a heterogeneous because the composition is no longer the same. Sour cream. The next two are actually kind of tricky. Sour cream, because of the fact that sour cream actually ends up settling out over time, there'll be water that floats to the top. Because of that, it's considered heterogeneous. Peanut butter over time does the exact same thing because of the fact that the oil floats up. So peanut butter is also considered heterogeneous. Sodium chloride is actually table salt, and that's a compound. Carbon dioxide is what you exhale, and that's also a compound. And finally we have oxygen. That is considered an element because it's right off the periodic table. So by looking at the physical and chemical properties, you can start looking at the physical and chemical changes. So if it's a physical change, it involves a physical property. If it's a chemical change, it involves a chemical property. Physical properties alter only the state or the appearance, whereas the chemical change will actually rearrange the atoms into different substances. When we're looking at physical changes, we're looking at extensive properties, where chemical changes look at intensive properties. Remember, extensive means the amount. With physical properties, we can easily change it back. Whereas with chemical, we have to do a chemical reaction to make it change back. A couple of things you might want to ask yourself during the process is it still the same thing when we're done? And can it easily be changed back? So these two here are what you're going to want to focus on when you start being asked if it's a chemical or physical change. For instance, melting butter. Because it's just melting, it's